Here we go. Section 1.1 and 1.2. It's going to take us a while to get through these. Today's, you're going to be like, why in the world? I already know how to graph a line. We talked about that yesterday. But we're going to just try to start our discussion of transformations in a way where you're just comparing it to something you already know how to do, so that you can sort of just think about graphing lines in a slightly different way. Okay, so we're going to talk about, is the pen going to work? There it goes, parent functions. And basically, instead of thinking of all the lines that you're ever going to draw as being their own line, like this line is different than this line, this line is different than this line. Yeah, that's still true, but they're all going to be kind of like the children of these certain parent functions. So, or actually just two. We're going to talk about, it's the most basic, the easiest, absolutely the easiest function that you can think of that looks like this one. So the two we're going to talk about are the constant function and the linear function. So the basic, easiest constant function there is just y equals 1. You know, all those y values are 1. The x's can be anything, but if you thought about the ordered pairs here, like every single ordered pair on this line, what is this? 1, 2, 3, 4. This is it. 4, 1. Like every single point on that line has a y value of 1. That's what they all have in common. We're going to start throwing in the function notation more and more. I'm sure you saw this in Algebra 1. Remember, you say f of x. For that, it's just a function of x. We're going to use whatever this x value is, plug it in, and get out some other answer, which here is always a constant of 1. But that's a parent function. And then every other constant function is some sort of derivation of that one. Same thing with a linear function. The easiest line that ever was is just when you do y equals 1x plus 0, or thinking of the slope 1 over 1. You know, it is just when you have a y-intercept of 0, rise of 1, run of 1. It's just going off at that 45-degree angle. That's the parent function for all the linear functions. Okay, and when we talk about the domain and range of them, domain, remember these are inputs, ranges are outputs. When we think about our coordinate plane, we have x's and y's. Our x's are our inputs, our y's are our outputs. So it's like, what all x's can you plug into this function? Well, you can plug anything in. Like if I said f of 7, it doesn't matter. The answer is always 1. It doesn't matter what x is. So my domain here is, I guess let's write it in words first. The domain here is all real numbers. And this, I'm assuming you've never done anything besides real numbers. Pretty much, if anybody's ever mentioned imaginary numbers to you, then you have heard about some number that's not a real number. Otherwise, every single number that you've ever thought about throughout school is a real number. We're going to add to that list this year, but you know, like this, any number you think of, that's a real number. So our domain, our inputs are all real numbers. That's what the x's can be. Our ranges, though, on this one, it's always 1. So we'd say our range is y equals 1. Now, I do want to talk about, you know, just because that's how we write things in the book, or, you know, like there's tons of different ways you can say that, or see it written down. Like some people might just put the symbol for real numbers, where it's a funky looking R where you double up the leg. And that's actually probably the easiest way. Some folks will go and put it directly in set notation. They'll say, okay, my domain is the set of all x's such that those x's are elements of the reals. So that's saying the same thing in a slightly more sophisticated manner, I guess you could say. For the ranges, same thing. We can just say y is 1. That's fine. Or you might see people go, okay, y is an element of the reals such that y is 1. Like they'll draw a line to represent the word such that. Or some folks will say that there's no reason to say y is an element of the reals, because unless you tell somebody otherwise, like maybe you just want to deal with the integers, then it would be important to tell somebody that y is an element of the integers. But since we're usually talking about the real numbers, a lot of folks think it's kind of redundant to say that every time. So they'll just say, okay, it's all the y's such that, and like where I did a line that first time, some people put a colon. It's the same thing. They both stand for such that y is 1. Now, we're not going to worry about getting all fancy in here. We're just going to say if the range is 1, we're going to say y is 1. If the domain is the set of all real numbers, we're going to put the symbol for the set of all real numbers. So same thing over here. If we're talking about domains, what can I plug into here? What all x's can I get on this graph? It's anything, all real numbers. But for this function, our range is also all real numbers. Because, if you plug a 20 in, you can get a 20 out. If you plug a negative 1/5 in, you'll get a negative 1/5 out. If you plug pi in, you'll get pi out. Like it's f of x. I plug in an x, I get out the same x. So we're going to just say, again, we're going to put the set of all reals. So because we're going to write it basically the simplest way we possibly can. Okay. But it's important, especially when you're taking standardized tests and whatnot, that when you see these slightly more, I don't know if you'd say sophisticated, but slightly fancier ways of writing it, that you don't worry about that it's all the same thing. Okay, so we're going to take those basic parent functions and we're going to transform them in some way. So we call these transformations. And transformations, they're going to change the size, the shape, the position, or the orientation of a graph. Okay, right. We're just completely going to just make something up because it's hard to show this really just using linear functions. So we're going to kind of get a little bit ahead of ourselves today. Like we're going to take an absolute value function, which I'm not going to worry about why it looks this way. We'll talk about that tomorrow. Again, I'm kind of thinking you may have graphed one of those last year. If you didn't, it's no big deal. We will start from scratch. And why does it look this way? But an absolute value function looks like a V, where the corner is down there at the origin. And so if we have this is a type of transformation. So all these are transformations. One type of transformation is a translation. So we can just pick it up and we can move it horizontally or vertically. But you don't change the size of it. Like it's going to be the exact same size V. It's going to be the exact same shape, and it's going to be the same orientation. So by orientation, I just mean that it's going to still open upward. So you could pick it up and move it, say, 4 places to the right. That would be a vertical shift 4 to the right. You could pick it up and, I don't know, move it down 2 places. And then you have a vertical shift down 2. You can do more than one of those things. You can pick it up and go 2 to the left and up 3 and move that graph to there. So that would be 2 vertical shifts, 1, 2 to the left and 1 up 3. And it doesn't matter which one you did first. It's going to end up right there. Okay, so that's a translation. We're just going to call those shifts. Okay. Vertical and horizontal. Today, we're only going to deal with vertical ones, though. We'll worry about adding a little bit more to it tomorrow. Like I said, I'm kind of getting a little bit ahead, so just talk about what the word translation means. There's going to be reflections. So let's say you took that same absolute value graph. It looks like this. If you flipped it over the x-axis so that, let's change color so you can tell the difference. Instead of it pointing up, you had it point down. But it's exactly the same shape. It's exactly the same size. We didn't shift it left or right. We literally just took it, picked it up, and flipped it over that x-axis. That would be a reflection about the x-axis. Our textbook says reflection in the x-axis. So just make sure that you're okay. Whether I say reflection in or reflection about, it does not matter. We're all saying the same thing. Different textbooks write it different ways. And so, don't worry so much about the author of my book says in. So Ms. Brandt's obviously wrong. Well, maybe Ms. Brandt just learned it from a different book. So you could do that. Maybe you could also, we'll take a different shape. Say we take this shape that looks like this, which is a parabolic shape. It's a quadratic, but it's not a quadratic because it's not a function. But If you took that and flipped it over the y-axis and had it look like this, that would be a reflection. So you can reflect things about the x-axis. You can reflect them about the y-axis. Either one, we're good to go. It's just you do not change anything about its size and shape. You're just changing its orientation. Okay, so those are called reflections. You can also just take and multiply the y values by a certain number so that you can either stretch a graph vertically or shrink a graph vertically. Let's do a good example. Like we'll take that absolute value graph again. Okay, and I'll actually put some points on there this time. So an absolute value graph is going to go through 1, 1, 3, 3, negative 2, 2. Oops, didn't look real good. So if I wanted to stretch this vertical, well, I guess we would say, stretch it vertically. And some people will say by a factor of blah, blah, blah. Like say by a factor of 3. Then what that means, everything is going to say, like right here, 0, 0. I took all the y values and I multiplied them by 3. So 0, 0 just stays put. Like that's not going anywhere. But 1, 1 instead will stretch to 1, 3. And 3, 3 would stretch all the way up here to 3, 9 because we'd be multiplying all the y values by 3. Negative 2, 2 would stretch to negative 2, 6. So it still keeps it. It's the same shape. Well, let's say it's the same shape. It's just stretched out. Like you're just actually, it gets. What's a good way to think about it? Like with the Play-Doh, if you've ever done that. Like if you've taken some Play-Doh and put it on a newspaper and then stretch that Play-Doh. It's the same picture. It's just stretched out. You can also take this original one and you can shrink it. You could shrink it vertically. Do a vertical. Let's try it. I'll do a different color. Hang on. Let's go with that one. So let's say it's a vertical shrink. Okay, and that's what our book says. They say shrink. I'll go ahead and tell you. Most books I've ever used call it a compression instead of a shrink. So you're just compressing it down, where it takes its original graph and then just kind of shoves it towards the x-axis. But again, it's just going to multiply all the y values by a certain number. So if you want to stretch it and make it skinnier, then you're multiplying the y values by a number bigger than 1. If you want to compress it and flatten it down, you'll multiply those y values by some number between 0 and 1. So like say we did, and people will do this, they'll say by a factor of maybe a half. So you take all these, 1, 1 would get squished down to 1, 1/2. And 3, 3 would get squished to 3, 3/2. And negative 2, 2 would get squished down to negative 2, 1. Because it would be half as high at each individual x value as it was before. Okay, so we call that a vertical shrink or compression. You know, if you make it, this one, for example, is getting skinnier. That would be a stretch. But the big thing is that when you take whatever that function is and you multiply its value, the y values, by a number bigger than 1, vertical stretch, a number between 0 and 1, a vertical shrink. All right, so here's what's going on these. I'm going to go through actually, how many examples are there? 1, 2, 3, 4, 5, 6. Okay, let's see which ones it says. Graph the parent function. Let's do that. If it tells us to graph the parent function, let's do that for every single one of these. So the parent function here is just the linear function. Y equals x. And I'm going to do these as dotted lines so that we can see it's a little easier to see that this is not our final product. That's the linear function for this g of x is x minus 4, just y equals x. The easiest possible linear function there is. Okay. This one, parent function to this also. y equals x. Just the linear function, parent function. Again, there it is. Okay, both of these. Yep. Same parent function, y equals x, just the linear function. Okay. Go ahead and get that on there again. Okay. This one, identify it, compare it to the graph of its parent function. Okay. So this, again, parent function. Y equals x. So they want us to compare that. What are we doing? Counting two at a time. Okay. Each direction. So again, we're going to compare that to parent function. Identify the function family to which this belongs. Compare it to the graph of the parent function, then identify the domain range. Okay. Now this is not a linear function, even though it is a line, but the linear functions have some slope to them. So this is a constant function. So the function family to which it belongs is the constant function family. Y equals 1 again. Oops, kind of missed the line right there. There's the parent, and then we'll go back and do the rest here in a second. Graph the functions and their parent functions. A parent function here, y equals x. So we'll just go ahead and get the parent on here. This one's the constant, y equals 1, so we're counting two at a time, which looks like we are. There's our parent function for this one. All right, so we got all these parent functions sitting there now. So we're just going to think about what they're asking us to do. And actually, hang on, before I may have skipped something. Oh, I did. Identify the function family to which this belongs. Again, the answer to that part is the linear function family. Okay. Now, all right, so think about what you do when you graph this line. Let's do a nice color. Let's do that bright pink. So if you've got g of x is x minus 4. Now remember, g of x, f of x, h of x, whatever of x, or it doesn't even have to be of x. It can be of t, of, whatever. Or it's just like a y. It's just we use x's and y's because so often we use a coordinate plane where the horizontal axis represents the x's and the vertical axis represents the y's, and we go from there. So this is just like y equals x minus 4. You know how to graph that. That's a y-intercept of -4 with a slope of 1. Okay, so there's that function. Basically, what they mean by these transformations is just describe what happened to the parent function, that dotted gray one, for it to become this hot pink one. Well, it just got shifted down 4 places. That is a vertical shift of going down 4. Now, technically, if you just say down 4, I'm going to be happy. But a lot of us, it'll say a vertical shift, or you could say the word translation. That's the same thing as a shift. So remember in our notes, that's what we had. A translation is a shift. But just describe what happened to it. You picked it up and moved it down 4 places. That's it. Nothing else. Okay? All right. This one. So think about what's going on here. If you have to graph that, you still have a y-intercept of 0. We got a slope of -1. So we're going down 1, right 1. There's that line. Compare it to that dotted gray line. It has the same slope. You didn't pick it up and move it up and down, side to side any, but all you did was take that gray line and flip it over the x-axis. So what this one is just a reflection in the x-axis. Now again, I wrote it like our book writes it. I usually say about the x-axis. It does not matter. A reflection in the x-axis, a reflection about the x-axis. All you do is get your point across. Okay? All right, this one, let's graph them both. We'll do this one in hot pink. Y equals 3x. Y-intercept is 0, slope of 3. Okay, so let's think about that. Did you move it up and down any? Well, no, they're both going through the origin, the dotted line and this hot pink one. Did you flip it over the x-axis? No, it was heading uphill in the parent function. It's heading uphill still. But what you did do is you went from the 0.11 to the 0.13. You multiplied that y value by 3. So for this, you have a vertical stretch. Now, if you want to say by a factor of 3, you can. I'm not going to worry about that. Just realize that that's what we can call that a vertical stretch. We're good. Okay, we'll pick a different color. Graphing this one, y-intercept is 0, rise 1, run 5. 1, 2, 3, 4, 5. Again, we're not moving it up and down any. We're not flipping it over an axis. All we're doing is it went from originally, this was at 1, 1. Now, if I plug a 1 into this, I'm at a fifth. It's a fifth as high as it was in the parent function. That is a vertical shrink or compression. Oops, didn't like a K very much. And if you want to say by a factor of 1/5, you totally can. You don't have to. But that just took the exact same line and it just shrunk all the y values at each particular x value. Okay? All right, this one. So we identified the function family. Well, parent function is y equals x, and we're going to compare it to what's there now. Okay. So first thing is just kind of check out what's going on. To get that downward slope, you'd have to flip it over the x-axis. So I'm going to kind of just walk through it one time. Like, let's say I flip it over the x-axis first. Okay. Ooh. Then it looks like that. Then, let's say the next thing that happens is that I want to move it up to where it is. So I pick that point up and I move it up 8 places. And now it looks like this. But they're too high. So then I've got to shrink them down so they're not so high. So I've got to shrink all the y values so that it lays right here on top of this. So this one's got 3 different transformations going on. It's reflected about the x-axis. It's moved up 8 spots. And it has a vertical shrink or compression. Okay, because it's a fourth as high as it would have been had it just been flipped and moved. Okay, and then they want to know the domain and range of this new function, what you're ending up with. Well, I can plug anything in the world into this. So it's all real numbers. I can get any number in the world out of that. Or you can look at the graph. Like, I don't care what x value you pick. There is going to be a y that lines up with it. And I don't care what y value you pick. There's going to be an x that associates with that y value. So, oops, I kind of made a mess of this. I'm just going to erase all that. So that's the sorts of things we're looking for there. Example 5. Let's see what we got next. We've got that constant, compare the graph, find the domain range. Well, let's go ahead and knock the domain range out. Your domain, your x can be anything. Your range, though, we are just getting out -3. And I'm putting y equals -3. If you had put, what do we call this one? F of x. If you put f of x equals -3, you'd be good to go there too. Okay. This one, there's actually a couple of ways you could describe this. I think the easiest possible way is just think about taking the line that's there. Well, there it sits. That's the parent function, right? And you just want to pick it up, go 1, 2, 3, 4 places down with it. So if I were describing this, I would just say it's a vertical shift that goes down 4 spots. Okay. That is the easiest. Now, one other thing you could do if you were, I guess, kind of a glutton for punishment, I guess it's not like you need to do this much. It's not, well, don't listen to me. It's not like this is a lot of work. But you could say that it's first. Oops, I lost that Y right there. You could say that first it's a stretch. Like I'm going to stretch it and get it to Y equals 3. And then I'm going to flip it over the x-axis. So I could have a vertical stretch followed by a reflection over the x-axis. So you could do that. Or the other way around. You could reflect it over the x-axis and then stretch it down 3 places. Or stretch it 3 places. Either one works. It doesn't matter. But definitely I would say just going down 4 places is hands down the easiest. Okay. All right. For this, let's see. Graph the functions and their parent functions. We got the parents on there. Describe the transformations and find the domain range. So this one we don't have to write out that it's a linear function. I think linear function for the first one, constant function for the second one. If we graph y equals x minus 7, let's see, maybe it's going to cross right there. All we just did is take that graph right there and we went down 7 places. So it's a vertical shift down 7. Domain, I can use any x in the world. Range, I can get out any y in the world. We're good. This one, f of x is -9. That's just like y equals -9. What's that going to be right here? Okay, I'm getting a little off again. Just pick that up. If it goes from 1 to -9, you moved it down 10. So that's what all I do. I'd say I move this down 10 spots. It's a vertical shift down 10. And domain, though, still anything. Range, still anything. And then we're good. Hope that helped.